Hi everyone, I would like to talk a little bit about where we are with analog computing at the moment and where we are heading to. And therefore I've prepared a set of 25 slides showing current areas of work and current problems that have to be solved to make analog computing a reality for the next couple of years. So where are we now? It is next to unbelievable how much analog computing has gained on interest in all areas of science. After the 1960s, 1970s, it looked like analog computers would be a technology of the past, something for the museum only. But in the last couple of years, it became more and more clear that digital computers are really facing physical barriers, which we will not overcome without doing substantial changes to the internal structure and architecture. Have a look at current CPUs, for example. It's quite funny. A couple of weeks ago, I found one of my first notebooks, which I bought in 2000. And this had a clock frequency of 3 gigahertz. And the notebook I'm currently sitting in front of has a clock frequency of 3.7 gigahertz. That's nearly 20 years ago, and next to no progress on this side. Of course, things became much faster with multi-cores and hyper-threading and whatever, but the sheer clock frequency, for example, is not easily beaten. The energy consumption of digital computers is horrendous. The main problem is cooling these machines. Having a look at today's thermal design power specifications for modern CPUs, you see that we have TDPs of about 150 to 200 watts per CPU. That's bordering on crazy, to be honest. Main memory is still an issue. It was an issue when I started with computing as an 11-year-old with my ZX81. Memory was the slowest thing on the machine, and the same today with about 80 nanoseconds to access main memory. So whatever is not in the first level cache will substantially slow down your computational progress. And the majority of chip area, if you have a look at the current CPU, is just not devoted to computing. Large areas of the CPU chip are just auxiliary functions like caching, cache control, bus control, register renaming, pipeline control, and whatever. Only a small portion of the chip is actually involved with doing real computations, which is a little bit of strange if you ask me. And more cores, it just does not scale, which everyone knows who has heard of Amdahl's law or has tried to program massively parallel computers. I started programming parallel computers back in the 1990s at my university in Mainz, where we had a large convex installation. And I realized that it is really, really difficult to parallelize even simple problems, since you will die in communications overhead between the nodes. And this clearly does not scale too well. And apart from this, as soon as you do your computations in binary, you run into problems of numerical stability, for example. And that's one of the examples I show my students. I ask my students, use a digital computer and whatever tool you like, and simulate a steel ball bouncing from a concrete floor. And many students just use a simple integration scheme like Euler integration, and they realize that the simulation gives not only it gives completely incorrect results. The ball is jumping higher and higher in such simulations, and they realize, oh heck, the integration method is of primary concern for everything I do with a digital computer. So we have a lot of problems with digital computing, and analog computing is one way of overcoming these problems on a basically. An analog Neumann problem with accessing memory from a control system and an arithmetic logic unit. And more or less all components of an analog computer are devoted to actual computations. There is nothing like a complex control system. We have a lot of individual computing components like summers, integrators, multipliers, etc., which we can use in a computation, and we have complete parallelism between all of these components. So the parallelism in an analog computer is much higher than in nearly every digital approach to this to these problems. And the energy efficiency, I have an example for this, of an analog computer is even also much better than the energy efficiency of a digital machine. And in my opinion, giving up the idea of representing values by binary numbers is a big advantage too, since you will get rid of the problems which typically haunt everything which is computing with floating point numbers. And last but not least, what we have is an analog world. With working with an analog computer guarantees you don't need any analog digital converters or digital analog converters. You can just interface to the real world and you have no stability problems. Of course, an analog computer does not use solutions which are as precise as solutions generated by digital computers, but in most cases, 3 or 4 decimal places are more than enough, especially for applications in engineering or machine learning and the like. And the big advantage of analog computers here is that you have no problems which are similar to numerical stability. Whatever you throw at an analog computer will always get at least a reasonable simulation result. Not a precise one, but never a simulation result which is completely off scale like the bouncing ball on a concrete floor. Let me give you a simple application example, which is a real application, not something I rigged up for this presentation, but something I'm currently working on with some colleagues from another university. These colleagues have a medical background and they are researching some intercellular pathways, communication paths between cells, which can be readily described by rather simple differential equations. The problem here is that they know the structure of the differential equations, but they don't know the parameters of the differential equations. So you have a set of differential equations. The real set is much more complicated than the one I'm showing here. That was just a proof of concept to demonstrate that it is feasible to apply an analog computer to this problem. Here we have a set of 4 coupled differential equations, which describe some reaction kinetics. And the problem is, while the structure is clear, we have a lot of parameters here. These are the k plus 1, k plus 2, k minus 2, ku, and so on. These are parameters describing the enzymatic reaction speeds taking place within the cell. So the problem is now you have a fixed set of equations, but you don't know the parameters. You have to do a parameter search. This is a 4-dimensional problem here. The real world problem has many more dimensions, but even this problem was quite impressive as we solved it in parallel on a hybrid computer and on a purely digital machine. And as you can see, this is the computer setup for the analog computer to machinize the 4 differential equations you have seen in the slide before. And it's pretty simple. All you need are 3 integrators. You have seen there are 4 differential equations, but there's a little trick. You can save 1 differential equation, simplifying the problem a bit. 1 multiplier and a couple of coefficient potentiometers. So you can use this setup to automatically search through a parameter space. And the search of the parameter space is done on this actual machine. This is one of the machines I have built, an analog paradigm model 1, a little bit bigger than the typical machines we build. And you see it is really a classical computer, nothing fancy, just a typical manual patch board and basic computing elements like integrators, summers, and multipliers. And this is part of the hybrid, of the digital side of this hybrid computer. The analog computer is used to simulate the behavior of this system of coupled differential equations, while a digital computer, which controls the analog computer, sets, for example, the values of the parameters. And what we do is just a search through a 4-dimensional parameter space to simulate the behavior of these differential equations for all possible settings within a given grid, which we will search through. You see that's pretty simple code, just 4 nested for loops. And this is all which is necessary to control the analog computer, which has, in this case, 8 digitally controlled potentiometers. And the results are quite interesting. It turned out that solving this problem and scanning through this 4-dimensional parameter space on a really high-performance digital machine with 48 cores running MATLAB, and solving the same problem on this hybrid computer showed that the hybrid computer was 33 times faster than the purely digital machine, and the results matched to an incredible degree. At first, I thought that I've mixed up the result files, but it turned out the analog results are nearly identical to the digital results. This speed up of a factor of 33 can even be made larger by changing the integration capacitors. It's definitely possible to reach a speed up of 330, and maybe even an additional factor of 10 is possible with slight changes to the structure of our integrators. And one of the most interesting points is that the overall power consumption of the analog computer itself was only 14 watts. And that's something where a digital computer just cannot compete with an analog machine. You've seen this machine is very classic. You have a manual patch board, which is a pity, so you cannot switch easily from one program to another. But in problems like this, where you have to search a multidimensional parameter space, that's not a problem at all, since one setup will be patched for a rather long time while you will scan through vast, highly dimensional parameter spaces. That was an example of what can be done already with an analog computer. And of course, I have thought about future applications and research, what has to be done to make analog computing a real option for the future. In the area of artificial intelligence, analog computers can be used, for example, to determine the synaptic weights, which typically leads to the solution of systems of coupled linear equations, which is not that simple as it turns out to use an analog computer for, since direct approach is unfeasible. You will end up with so-called algebraic loops where you have summers feeding summers feeding summers, which will yield unstable results. What you can use analog computers for also is you can simulate parts of the real world to train classic digital neural nets. I'm currently working on an example in this area together with a friend where we are going to train an artificial neural network which will control a simple mechanical process, but the mechanical process itself is modeled on an analog computer. So you can, for example, insert perturbations pretty easily on the analog part and see how the trained artificial neural network will respond to these. And you can change parameters, for example, check how will the artificial neural network operate this mechanical model if, for example, the gravitational force is increased or whatever. The idea is to have the analog computer do the simulation of the real world in a sped up version. Using different timescale factors for the integrators makes it easy to simulate a real complicated mechanical system 10, 100, or 1,000 times faster than in reality, and use the behavior of this system to train the neural network. Another application of analog computers in this area is to use the analog computer to implement the actual artificial neural network. This is also very, very interesting. Let me give you some insight into the not so simple problem of solving coupled linear equations. Coupled linear equations are easy at first sight, but as we all know, simple Gauss or Gauss-Jordan elimination is not a good idea when it comes to a digital computer. You would use something like LU decomposition or the like. And the idea of using an analog computer is not new, but in the decades before, it was not feasible, since you need lots and lots of computing elements to do this. With modern technology, it is possible to devise analog computers which have hundreds or thousands of integrators to solve even complex linear equation systems. Have a look at a not very clever approach to this. You could transform your set of linear equations here, as an example, a set of two linear equations with two unknowns is shown, which has been mechanized on an analog computer directly. And what you get is, as you can see, an algebraic loop. You have an even number of summers which feed each other, and of course, this will not yield a stable solution, though this just does not work. It's interesting if you have, when you have a look at the literature. most authors will suggest, okay, transform your set of linear equations into a set of coupled differential equations and then solve these differential equations. The basic idea is not bad, but the problem is if you do it on a one-by-one basis, you will end up with a set of differential equations which will not converge reliably. A simple approach would be something like an iterative system, iterative approach on a digital computer to transform your set of differential of linear equations into in matrix notation into a set of differential equations. Ax minus b equals epsilon, and your epsilon is the error you made. And then you don't iterate, but you wait for the solution of these of the set of coupled differential equations to converge to something. The problem is, when you have a deeper look at it, you will see that the roots of the characteristic equations all have to be greater 0 in order to have this system of differential equations converge to a solution stably, and this is typically not the case. And that's a real problem. Many articles about solving linear systems of linear equations on analog computers just stop here and say that's how to do it. But this will not yield stable results, as this example shows. That's a very simple system of 3 linear equations, which I have transformed into a set of 3 coupled differential equations. And as you can see, that's not converging anywhere. Only x2 is converging, and even this value is, of course, completely off scale, since x1 and x3 are wrong and overload. There's an interesting trick, which is also not new but not well known, to transform your system into a Hermitian system by multiplying the left and the right-hand sides by the transpose of your matrix of the linear system. The problem is you will either need a digital computer in the first place to compute the new matrix ATA, idiotic, since you could solve your equations on the digital computer anyway, or you will need very, very many analog computing elements. But if that's not longer a problem with modern, maybe on-chip analog computers, this approach yields very stable and very quickly converging behavior of the solution of coupled linear equations, which is pretty interesting. That's the same set of equations, only transformed by multiplying from the left with the transposed of A, and you see this settles very quickly on a stable result set. That's, I think, a really interesting application of analog computing, but it shows that many of the papers which are currently available on this topic, they are looking for a problem to solve with an analog computer, but sometimes it did not look deep enough to really see the problems with an analog solution for this type of problems. At first view, it seems a little bit perverse to transform a simple problem like solving a set of coupled linear equations into a set of coupled differential equations, and then even doing this with a really complicated matrix like ATA. But on second thought, it is a really clever approach to solve this problem. But you will need a lot of computing elements and 2 times the quadratic of the size of the matrix as coefficient potentiometers, and that's still some kind of a problem. The main problem regarding the acceptance of analog computing or analog computers for future applications is the classical patch panel. We have to get rid of this patch panel. That's too inflexible and it's expensive too. You have hundreds or thousands of plugs and jacks. You need the cabling. You have problems with the cables. You cannot switch between programs easily. It is a real mess. The problem is it is not simple to devise a suitable so-called auto patch. The idea of an automatically reconfigurable analog computer is by no means new. This was pioneered by Mr. Hanauer in the late 1960s, early 1970s, with his so-called Hanauer matrices. But the problem back then is the same problem as now. You need an incredible amount of relays to build your switch matrices. Back then, that was a study done for NASA. They equipped an EAI 680 precision analog computer with the so-called auto-patch system, which required, as far as I know, about 40,000 read relay contacts. That's, of course, not feasible. Even today, that would be a real problem. A problem here is we still have no real idea how to tackle this problem. Is it a good idea to have, for example, a sea of gates, which is then interconnected by means of a gigantic crossbar switch? Or would it be more clever to devise analog macro cells, with each macro cell containing at least one integrator, multiplier, summer, whatever? So you have more complex macro cells with the idea of decreasing the number of interconnections necessary between the various macro cells. Here, really, research is necessary. What we need is a library of typical application programs so that we can devise a structure for macro cells which would allow one to devise an auto-patch analog computer which requires a minimal amount of switch points. The problem with switch points is what technology should be used to implement the switches. Relays are, of course, not an option. FET switches, maybe switches on the basis of flash memory cells, a very interesting idea. I think memristors are not of interest here as they will change their characteristics depending on the current flowing through them. What should we use as switches? I am personally currently researching into using video switches for this purpose. There are some interesting integrated circuits for applications in video matrices, which seem to be rather well suited for analog computing applications as well, but this is also an ongoing research area. There's at least one company which uses switched capacitors instead of a switching matrix, but if you ask me, that's not the best idea since you lose your continuous time. So you switch from continuous time to a discrete time system, and you are more or less back where you would be with a digital computer. So there's a lot of open questions regarding automatically reconfigurable computers on the hardware side. The problem is the software side is as complicated as the hardware side, since what we would need is some kind of a compiler, or even maybe synthesizer might be a better word, as in the FPGA world, where we can transform automatically a set of equations into a suitable setup of the analog computer. And what we would need is a real software ecosystem. We need a language, we need methods to do the scaling, ideally automatically. We need algorithms to minimize the number of computing elements. Really complex problem. Next point we have to talk about is hybrid computing. An analog computer itself may be a joy forever, which is definitely true, but without a hybrid computer, its control is pretty complicated. And as you have seen, even simple problems like searching through a higher dimensional parameter space requires some digital control of the parameters used by an analog computation. So hybrid computing, one of the questions that will crop up is, can we use an analog computer to guess good estimation and a good approximation to a solution of a problem, and then feed this into a numerical algorithm to refine the solution? I have no clear sight of what has already been done in this area. Can we use a hybrid computer for automatic rescaling? It could be just throw an unscaled set of equations onto an analog computer and let it run and see when a computing element either overloads or has too little values at its output, so that noise will wipe out the real results. When an overflow occurs, the digital part of the hybrid computer could halt the computation, read out the values, do an automatic rescaling, and then feed back new values for the coefficients for the analog setup to the analog computer and continue the computation from this point. This would be, in my opinion, very, very interesting. You could have maybe really the benefits of floating point number by this approach, having a digital computer checking for overflows, halting the simulation run and rescaling the problem without throwing away the results obtained until there. Another application for hybrid computers is, of course, the solution of partial differential equations, which are notoriously difficult for a classic analog computer. I'm not talking about direct analogies. There's a lot of research going on in this area, but the classic analog computer, of course, has real problems with partial differential equations, since time is the only free variable you have. And if you have a differential equation involving not only time but x, y, and z, you have to discretize the problem, which requires a lot of computing elements. And one approach could be just implement one, maybe macro cell on a classic analog computer and do the discretization on the digital part, feeding one set of input values to this so-called maybe macro cell, let it compute, read out the results, and feed it back into the same macro cell. This could make it possible to apply a classic analog computer to partial differential equations. And one large area of application, of course, is using the analog computer to do pre-processing of data. Measurement data, data from medical sciences, and so on. And analog computers, of course, ideally suited for this, and there was quite a lot of research in the 1970s and even the 1980s in neurophysiology and neurosurgery, where they used here in Germany at the university a large Telefunken analog computer installation to pre-process EEG data during a surgical procedure and warn the surgeon if certain criteria were met and maybe he cut too deep or whatever. This was much faster and interfaces very easily to biological systems, of course. So what I already have mentioned is the problem of a software ecosystem. I think this may be the most difficult problem to solve. Just building hardware is not that hard. But what we need is a programming language. My current approach with my hybrid computer is I use C to control a microcontroller, which controls digitally settable potentiometers in the analog computer. But I need a patch panel to implement the program on the analog side. What we need is a real programming language which allows us to program the analog side as well as the digital side without an impedance mismatch between programming the analog and digital side. So we need a language, we need a software ecosystem, we need libraries, we need a compiler, we need optimizers to create the bit streams required for setting the switches in the auto patch panel, and as I already told, maybe even implement automatic scaling processes. I think this is a very, very important topic, and I would like to encourage all students interested in compiler writing and whatever to have a look at this area. So, components and implementation. Not much has changed since the early days of analog computing. Our components have become better and better, not the capacitors, that's a real pity, but operational amplifiers are really good, not as good as some of the classic operational amplifiers. If you have a look at the tiny phase shifts exhibited by transistorized operational amplifiers like those applied by Telefunken in the 1960s, 1970s, you will see that the phase shift and the open loop gain is still better than those of most current operational amplifiers. But modern operational amplifiers have enough open loop gain to be used without complicated drift stabilization schemes and choppers as the heart of integrators and the like. But what about memristors? Could we use memristors instead of capacitors to implement integrators? This would be very interesting, since a memristor could be implemented much more easily on an integrated circuit than a classical capacitor. Another question, could we use memristors elsewhere? Maybe as switching elements. I personally doubt it, but I'm by no means an expert in memristive devices. Or could we use, for example, floating gate transistors like those used in flash memories as switches or as coefficient units? There's, I think, a lot of different ideas where we can employ modern hardware to implement new analog computers, maybe even new computing elements. A quick note here. I have a friend who runs a rather big company here in Germany, and he is a sputtering apparatus at his company. And he has offered, if someone is interested in implementing memristors using his infrastructure, he's welcome. So if anyone is interested in doing some basic memristor research, maybe with the option of having a product at the end, chips or wafers with memristors for experimentation or even for commercial applications, please let me know. I will put you into contact with my friend. So what I have not talked about, because I'm not an expert on this, are direct analogies. What I've been talking about are indirect analog computers consisting of summers, integrators, multipliers, and the like, where you have an electronic model of your mathematical problem. A direct analog computer could be based on nearly everything, resistive pads, electrolytic tanks, and the like, and these machines would be far better suited, for example, for solving partial differential equations. But in this area, we are much far away from something like an auto patch or even the idea of a software ecosystem. But it would be very interesting to do more research in direct analog computers. How could we parameterize these? If you have a look at classical electrolytic tanks, these were a mess to parameterize, but the results you get are really astonishing. What technologies could we use? A classic electrolytical tank is not a good idea. Maybe a grid made of memristors instead. There's a lot to do. And yet another area where research is required are digital differential analyzers. I personally will, I think, always prefer an electronic analog computer due to the non-binary value representation. But a digital differential analyzer has the advantage that we already more or less have our software ecosystem. What we have are languages like VHDL, where we can describe the setup of a digital differential analyzer and just load the synthesized bitstream files into an FPGA, which then implements the DDA. What we can definitely rule out are the very classic approaches of a digital differential analyzer like MIT-IDA or the Bendix systems, which just have one arithmetic logic unit, which is then time shared between the various computational elements of the DDA. I'm pretty sure that a modern approach to DDAs would involve a field programmable gate arrays, which will be then reconfigured to implement the various problems that should be solved. The question which is cropping up here is, would it be feasible to either develop a general purpose DDA with a fixed structure on the FPGA, which could be then implemented in form of an ASIC or some other custom specific integrated circuit, or should we describe the problem in some meta language, which is then compiled into VHDL and yields an FPGA setup which is specifically tailored to solve the problem under investigation at the moment? Both approaches are, I think, feasible. The second approach is maybe the more general one, but would require that you always have access to the FPGA development tools, which may be a problem for licensing, language, whatever. I have a very simple conclusion to these points. There's a lot of work to do. Let's get started. We need to solve these problems to have a chance to place our beloved analog computers as a real competitive machine to the currently prevailing digital machines. We are lacking on so many areas, especially the software ecosystem, that currently analog computing is something for specialists. What we need is a software ecosystem to make these approachable to the layperson, someone who has just studied computer science and not studied analog electronics or mathematics. We can't bother the users with the intricacies of an analog computer. We have to abstract from the real machine and make it blend into a digital environment. Thank you very much for your interest.
Thank you very much, Dr. Ulmann. It was very interesting. Thank you. I would have only one question, which is quite basic question, but I think this is important. The important thing is that you already told us a few times that about precision of doing analog computation.
Yes.
But the question is, everybody, I would imagine, would ask, what is the difference in the if you calculate whatever problem you calculate using the digital computer, and if you do the same using the analog machine? What will be the difference between the precision of the results?
The difference is huge. If you compute on a digital machine with single precision floating point values, you have about 7 decimal digits. If you use double precision floating point, you have 15, 16 decimal digits. Solving a problem on an analog computer will yield 4 decimal places at the most. But the problem is, why do we need such a high degree of precision in digital computing in the first place? Nearly all problems that we tackle have parameters that we just don't know to more than a couple of decimal digits. So what we need the high precision of floating points, either single or double precision numbers for, is the numerical algorithms require this precision. If you run classic numerical algorithms on a machine which would offer only 4 decimal digits of precision, the results would be complete garbage. An analog computer does not have the problem. You only have a very limited amount of precision, but you always have a reasonable result, since an analog computer does not work in a numerical, classical step-by-step fashion. So the very low numerical precision of an analog computer has, at least in my work and the work of colleagues, never been a problem at all.
Can I buy one?
Of course, you can buy one. The machine you have seen, we have currently, my wife and I, sold several of these machines to universities. 2 of them are used for teaching, and some of them are used for actual research, as the one machine I've shown in medical research. But you can, of course, also build one. Building an analog computer is not too difficult. It would be a great project for students for a bachelor thesis or the like.
Yeah, well, with digital computers, you know, the story went this way, that one day everyone could buy in the store a small computer and use it. I think that was the explosion for computers.
Yes.
Because in before, you know, at universities or whatever, you know, army labs, they use computers, the digital computers, but at a certain moment of time you could just buy it in the corner store.
Yes.
And that was the explosion for computers and computing and everything.
That's
so
right.
So I do think that this analog stuff is great stuff. Absolutely, I'm convinced, and I don't want to present here my arguments for that, but the point is that if the people would not grab it and use it in the telephones or whatever, then it will be really difficult to start and to move.
That's right. At the moment, we are not there. That's really a problem, but we will be there. There are several approaches in the United States to develop analog computers on chip. which have their own share of problems with regard to parts precision, how good can you match resistors or capacitors on a chip, for example. So at the moment, an analog computer is a rarity, and its application area is somewhere where typical numerical algorithms either don't converge or they are just too slow. But you are right, we have to get to a point where an analog computer is just an integrated circuit, ideally with the analog digital and digital analog computers contained on the chip, which will plug in as an extension card in your computer as a coprocessor. Correct.
Mm-hmm. Yeah, I agree with that. But if you think, for example, about physics, then to me, I'm a physicist. To me, physics is analog.
Yes,
everything is analog in
the
physics.
world is analog.
And then suddenly everybody is making this damn thing digital, you know.
Yes.
Even there are books about the digital universe, you know, as the nature is doing calculations up there, you know, and solving in the digital way differential equations about, you know, gravity, whatever is there.
Yeah.
So when I read something like that, I'm kind of like, oh no, that it can't be like that. That there's a God is sitting on the cloud and doing digital calculations. It's not physics. It's not the nature. And this is precisely where the analog computing and thinking goes in. You know, that you have input, output, and something very nice happening in between.
Yes.
And it's happening in such a natural way that the digital people, they cannot even imagine.
Yes, definitely.
Because they have to have so many things in this digital computer, you know, it's just incredible amount of stuff there. But in analog calculations is very straightforward, just in, out, and that's it.
Yes,
except all the problems which you just told us, of course.
Yeah. But maybe you have seen my latest application note solving the one-dimensional time invariant Schrödinger equation on an analog computer. 2 integrators and a multiplier, and you get solutions of the one-dimensional Schrödinger equation.
I think I have seen this. Where did you publish this paper?
It's on analogparadigm.com under documentation.
Okay. I think but okay. But then there is another thing which is also going in my head, is the relationship between the analog computation and the artificial networks.
Yes.
To me, it's almost the same. As far as I can see, it's almost the same. Sure, there are some, but you know, because using these artificial networks, you know, you can teach them to solve your one-dimensional, you know, Schrödinger equation, and then you just have just input and output.
Yes.
And it goes just in 1 second. You are not solving this, you know, differential equation. It's just in out, because you spend a good time to teach the network to respond to input and then to get. But this is the case also with the analog computing of this kind of.
Yes, it's ideally suited to implement artificial neural networks. By the way, what I did not mention, it might be interesting if someone is interested in implementing artificial neural networks with electronic non-digital means, might be to have a look at stochastic computing.
Exactly.
That's pretty interesting, I think.
Mm-hmm. Yes. All right. I have seen the paper from, it was just about this meme stores and the analog computing. It was just two months ago. Not the guys from Spain. I can't recall their names right now. But that was on Archives in Physics published. Okay. I will send you a link to this paper.
Yes, this would be great.
And they provided analysis how to solve differential equations with those meme stores, and the analysis of how precisely they can, you know, get the results. Okay. So I will send you a link to this paper because it was very nice paper.
Yeah, that would be very interesting. Thank you very much.
All right. Okay, Dr. Ulmann. So thank you very much.